Okay, good morning, guys. So what I'm going to do here, or I guess this little experiment is something that I talked about with you guys in our virtual classroom, and it was in relation to strength of magnetic fields and the differences between an AC magnetic field and a DC magnetic field. So what I've done, this is a braking system that would be applied to like a shaft of a motor. It's a magnetic brake. Not something that has been used in a long time, something more for just our demonstration purposes. This is that core material that I was showing you guys before in the Learning Hub with the laminated core, and it's got a little copper ring there. That copper ring there, the purpose of that is to focus the magnetic flux field that's being generated by the electromagnet to ensure that it meets up properly. This is something that in motor control we call a shading coil, even though technically it has no electrical connection to it because it's not conductive to current in this case, but what it's doing is it's acting like the nozzle of a hose, and it's focusing the flux that's being passed through this core material so it meets up properly with the rest of the magnetic circuit, so to speak. So the purpose of this guy, if I insert that core in there, it's now mounted via some rolling bearings up here, and once this thing energizes, it's going to pull down, and what that would then end up doing would be applying tension to this braking component here, and you can adjust that via the spring here. That's not the working part of it that I really even care about. It's more watching what happens when this pulls up and down. So we have this connected up in an AC circuit right now. So I've got a voltmeter here on the left, I've got an ammeter here connected in line on the right to measure the voltage and the current. It's going to be quite noisy. You're going to hear that magnetic hum when this thing starts to engage. When it's under voltage, it's rated at at least 120 volts in order to start to energize it and actually have it pull down. So we'll just keep an eye on the voltage here and see what happens, how much voltage it takes to pull that in, and how much current it's actually going to do to overcome that resistance of that movement. Once it does pull in, you'll see the current is going to shoot down, way down to next to nothing because the magnetic circuit's complete. So let's fire this guy up and we'll have a look what happens. And once again, just a reminder, it's going to be a little noisy to start with here. So we're at about 7 volts with no activity. We're at 12 volts and about 1.5 amps with no activity. We're at 20 volts and 2.5 amps, no activity. We're at about 30 volts and almost 4 amps with no activity, but it's humming. And we're at 40, 45 with 5 amps. And we're at 77 volts or something, and now we're down to like 6 amp or 0.6 amps. We can just keep increasing it up, and it's not going to have any further difference. When we relax the voltage a little bit, you're going to see that the magnetic field lets go and it allows that thing to spring back out again. Okay? If I energize this up, sorry, I'm just going to take this guy out. Okay? If I energize it so it's sealed, see now that core material is already in there. So I'm at about 70 volts or so. I can pretty easily pull that core material up with very limited effort. Okay, I can break that magnetic field quite easily because the constant changing of polarities between positive and negative in our flux lines. So those domains are always constantly being scattered back and forth, and in doing so, what that ends up happening is I'm able to break the flux a lot easier with that core material and pull that out. So I'm just going to reset this. I'm going to move these items over to our variable DC. And I got to change my meters over to DC. Okay. And what you're going to find is that because DC provides a stronger magnetic field, because the polarity of the current is in the same direction at all times, meaning that the magnetic polarity that's created by the turns of the conductor around that coil, they're going to create a constant north and a constant south. So you're going to find that it takes a lot less voltage and current to energize that and pull it in, and it's going to be very difficult for me to try to break that. Okay, so let's just turn this guy on. We're at 0 and 0 right now. We're going to energize it up. We're at 7 volts DC, 3.5 amps. Oh, see, 15 volts DC. We can probably even go less than that. 10 volts, 5 amps. And it's being held strong. More current to hold it that way though than what we saw in AC. Okay, but even at 5 volts or 4 volts or 2 volts or 1 volt, you're seeing that it is being still held in place. Okay, so what I'm going to do is I'm just going to shut that off right now, and then you see it pop up. I'm just going to take this guy out. It's already sealed. I left that at about 1 volt DC, so I'm going to turn that on, and we're going to see that we got 1.2 volts and half an amp in DC. Okay, and I physically, it takes a lot of work to pull that out, but I can break it. But wow, that's a lot stronger of a magnetic field than it was in AC. If we flip this back to AC and I show you the difference once again, we're just going to go back to AC. We'll click that back to AC. Okay, I'm at that roughly 1 volt. Actually now it's about 3 volts AC, and literally it takes no effort at all to break that. So that was the purpose of this lab, was just to sort of show you guys the difference between AC and DC magnetic fields, and that a DC magnetic field will always be stronger. But as we talked about yesterday in the Learning Hub, the difference with, or why we tend to use AC versus DC, is because with AC we can transform voltages up and down really easily because of the constant changing of the polarities. It doesn't oppose that change nearly as much as it would in DC. Okay, so that's what this video was sort of intended to showcase. Thanks.